So the Lie groups, in addition to having a group structure, also has a differentiable manifold structure because each element in the Lie group is parameterized by a few real numbers, such as in the rotation groups is specified by the rotation angles and so on. So those parameters can occupy values within the continuous range. And so these are also called continuous groups. So Lie groups are, by definition, continuous groups. Besides the continuous groups or besides the Lie groups, you also have certain discrete groups which are of importance in physics. You have the crystallographic groups where you have the rotations by fixed angles and so on and so forth. But if we have time, I don't know if we have time later on in this course, probably the discrete groups which are of most importance in physics are the so-called symmetry groups. A particular symmetry group, or symmetric group, I should say, not symmetry, symmetric group, Sn, is the set of permutations of n objects. Okay, so since given a number n of objects, there are n factorial ways to permute those objects. A symmetric group with fixed n has n factorial elements in it. And you can interpret the identity as being the permutation that does nothing to the original order of the n things. And then, of course, you can multiply one permutation by another by simply performing the permutations in sequence. Okay, so you do a first permutation first and then a second permutation, you end up with another permutation. So multiplying two things by the simple order of permuting things forms the basic multiplication process in the symmetric group. And now, this group is of importance in physics because of a very specific reason. In quantum mechanics, you know that elementary particles are, so to speak, indistinguishable. So if we are talking about, let's say we are talking about n electrons. So you take the lithium atom, for example, okay? And outside of the lithium nucleus, there are 3 electrons. So how do you describe a particular state of this lithium atom? You describe it by wave function. But you see, out of these 3 electrons, you cannot tell which one is which. Because in quantum mechanics, ultimately, the particles are indistinguishable, so to speak, unlike the case of classical mechanics. Now, you think about it, you probably understand what I mean. Classical mechanics gives you the intuitive picture, at least intuitive understanding, that you can make a mark on each of the electrons, right? You can imagine painting one of the electrons green and one of the electrons blue and the other one red and something like that, and at least you can theoretically distinguish the electrons by following their different trajectories, right? Even though the trajectories may be very complicated, you can think of the green electron as following its trajectory, the red electron as following its own trajectory, and the blue electron as following its own trajectory, and so on and so forth. Classically, you can think of the electrons that way. Quantum mechanically, you cannot. Why? Because of the uncertainty principle. Okay? Because following the electron's trajectory means precisely that you can know the position and momentum of the electron simultaneously, arbitrarily, accurately at a particular instant in time. And that's precisely what the uncertainty principle forbids you to do. Okay? So in quantum mechanics, you cannot think of this independent trajectories of the 3 distinct electrons. It means you can no longer tell them apart. Okay, you can no longer even theoretically paint them blue, green, and red. What that means is that the wave function, which has the coordinates of the 3 electrons in there, would have to obey a certain kind of symmetry principle when you interchange, when you permute those electrons. And it turns out in quantum mechanics, now this is actually a result that follows from special relativity, that there's a deep connection between what's called statistics and spin. It's called the spin statistics theorem, which I totally cannot prove it to you at this time. But let me just mention this. What it says is that particles of half-integer spin would obey what is called Fermi statistics, and particles of integer spins would have to obey what's called Bose-Einstein statistics. These two are very different kinds of statistics. Fermi statistics means that if you interchange any two particles, you change the sign of the wave function, anti-symmetric wave functions. Bose-Einstein statistics means that if you interchange two particles, permute two particles, you leave the wave function unchanged, symmetric with respect to interchange. So one is anti-symmetric, one is symmetric. With respect to all kinds of dynamical variables, okay, including the spin variables. Now, I cannot go into the details at this point, but what this has is very, very serious, severe consequence on the behavior of these two different kinds of particles. On the one hand, Fermi particles are the kind of particles where you can only put one of those particles in a particular quantum state. This is called a Pauli's exclusion principle, right? Bose particles, on the other hand, are particles where you can put as many particles as you want in a particular quantum state, okay? So if each of us is a fermion, and let's say if each chair represents a particular quantum state, only one of you can sit on the chair at a time. If you were all fermions, all of you can sit on the same chair, okay? That leads to very, very different physical behavior among all particles. Just about the deepest consequence that you can have. In terms of connection between spin and statistics, okay? So when you talk about, let's say, a wave function of fermions, let's say, so all those have to, as I said, the wave functions have to be totally anti-symmetric with respect to interchange of any particles at all. Then what you have to do is ultimately understand the so-called irreducible representations of the symmetric group, okay? Because that would tell you, basically, sort of without solving the Schrödinger equation explicitly, and many times, as soon as you get to even a 2-electron atom, the solution of the Schrödinger equation becomes tremendously complicated, not to speak of the lithium atom, which is a 3-electron atom. And of course, for some of the higher electron number, atomic number atoms, it is useful to be able to come up with a method that can allow you to identify the different energy levels of that particular atom, okay, leading to what are called exclusion principles and so on and so forth. Very important in spectroscopy. Basically tells you what kinds of states are possible in a multi-electron atom if you succeed in finding all the irreducible representations of the symmetric group. Now, obviously, this mathematical problem is not only important in atomic physics, it's important in nuclear physics also, because in the nuclei, similarly, there are a number of identical nucleons, so many neutrons and so many protons and so on and so forth, and ultimately to all problems in elementary particles, where basically you're talking about a system of certain kinds of particles, and within each kind, all the particles are indistinguishable. Okay? All right. Now, we will spend most of the time in this course talking about the Lie groups. If we had to bring in the symmetric groups also, unfortunately, it would probably take up the rest of the course. We don't have time to do that, although it's a tremendously interesting as well as important problem, because the two problems are very closely interrelated. Finding the irreducible representations of the SUN groups, the Lie groups, very closely connected to, I should say, finding the irreducible representations of the symmetric groups, okay? And so this is ultimately a very important problem in physics, although we'll only be able to look at kind of only one half of it to speak of, not even one half of it, maybe about 1% of it, only for the even for just the continuous case, because there are all sorts of different interesting stories for representations of different groups and so on and so forth. We will do the SON, not the group representation so much, but the representations of the associated Lie algebra, okay? Because as we'll see, that leads to the important commutations of the angular momentum operators that you will learn or have learned already in quantum mechanics, those important commutation relations, Lx, Ly giving Lz, and so on and so forth. All those things will come from an understanding of the representations of the Lie algebra. That's our next step. But before we get to there, let me just mention a couple more general concepts on basic group theory first. So the next concept, there are really just two more. After we have introduced the fundamental definition, mathematical definition of a group, then we'll look at the so-called concept of a group homomorphism, and then we'll discuss the concept of group representation. Okay, you'll find that we'll be using these terms quite often as we go on in the course. So let's say you're given a group. Let's say you're given two groups, G and G prime. So a group homomorphism between the two groups, G and G prime, is a mapping from one group G to another group G prime, which can be totally different groups, okay? The mapping has to satisfy one condition. And if the mapping satisfies that one condition, that mapping is called a group homomorphism between the two groups. Now, this definition is in the notes, so you don't have to copy it down. In general, in mathematics, a homomorphism is understood to be some kind of mapping that preserves the structure of the two different things that are being mapped between, okay? So now, this mapping does not have to be a one-to-one mapping. It certainly can be a many-to-one mapping, and as you'll see, we'll be discussing specific homomorphisms which are two-to-one, and so on and so forth. But it has to satisfy the so-called preservation of structure property, which says that if G1 and G2 are any two elements in the first group G, then and the product G1, G2 written in this order is equal to some other element, let's say G3 in the same group G, then it has to be true that f of G1, which now becomes something in this group, okay, multiplied by f of G2, which will be something else in this group. And so it makes sense to talk about the multiplication between those two things since this is a group. And guess what? Will have to be equal to f of G3. Okay, this is a so-called group homomorphism property. Now, let me try to draw a picture so that you kind of maybe have a pictorial understanding better of what we mean by that. Let's say these are two completely different groups, okay? And there's some mapping between the two, all right? The mapping has this property. Let's say this is G1 in here in the first group, G2 in here in the first group, and this is G3, which is equal to G1, G2, like so, okay? So using this map, if it's a homomorphism, it will be like this. This one gets mapped to f of G1, right, by this homomorphism f. And this 2 gets mapped to f of G2, right, like so. And this one gets mapped to something else. The requirement is that where does it get mapped to? It gets mapped to f of G1 times G2. In other words, f of G3. Okay, not all maps obviously satisfy this property, right? It has to, the technical term is or the descriptive term is, a group homomorphism preserves the multiplicative structure of the two groups, okay? If this times that gives that, then the mapped result of this times the map result of the second one gives the map result of the third one, so on and so forth. Okay? Now, it is important to understand that the way I've drawn it, it's a one-to-one mapping, but it does not have to be so. Okay? You can have a many-to-one mapping if this is if this equation is true, then you have a group homomorphism. Now, immediately you can think of an absolutely trivial homomorphism, right? Can you think of the simplest homomorphism? Let me just tell you what that is. It's absolutely simple, absolutely trivial, and so we don't have much use for it, but mathematically, it is still perfectly legitimately a group homomorphism. Let's say this is a group G, this is group G prime. If this is a group, it has its identity element. Let me call this E prime, okay? All right. Now, supposing I tell you this is a map we are going to be working with. Everything in here gets mapped to this one thing in here. So obviously, this is a many-to-one mapping. Okay, it's not a one-to-one mapping. Okay, but hey, it satisfies this property. Obviously, think about it just for 1 second. Okay, it satisfies this property. So therefore, this is legitimately a perfectly good group homomorphism, although it's an absolutely trivial group homomorphism also. Okay? Yeah?
Are there some groups where you can map back from G prime back to G?
No, we're talking about always from one to another, one direction of the map. Okay? Obviously, there's no inverse mapping. Because if it's a many-to-one mapping, by definition, there's no inverse mapping. The map is not invertible. Because inverse mapping means that you can tell exactly where this one is getting mapped back to. But if it's a many-to-one mapping, then you've lost all memory of where you got mapped from in the first place. Which of these? Can't tell. Okay? So a many-to-one mapping is, by definition, not an invertible mapping. Okay? Okay. So this is a group representation. Group homomorphism. Now, another fact perhaps is this, that let me see if this is true. Okay. Let's say the identity element in this group and G prime, and this is E prime is the identity element in the other group. The two identity elements are different, of course. Okay, it's just the identity. This one may be n by 5 by 5 matrix. This one may be a group of 2 by 2 matrices. So the identity elements are very different. One is the 5 by 5 identity matrix, and the other one is the 2 by 2 identity matrix. Okay, but let's see. Question is, under group homomorphism, where does this get mapped to? Okay, so you can always write the identity as some G times G inverse in this group. Okay, and and this get mapped to. You ask the question, what does this get mapped to? If F is a group homomorphism, so now G times G inverse is always equal to E, right? So this gets mapped to Fg times F of G inverse. Okay. Fg times Fg inverse. And what is that equal to? Okay, let me see. I'm trying to say that this is always E prime. The inverse of F of G. Yeah, that's correct. The last term, and you can prove that also. Okay. The last term is the inverse of the group element Fg, and that's always equal to E prime. Okay? I'll let you prove that. Okay? So for group homomorphism, identity is always mapped to identity. Okay? Like so. Okay, now let's next talk about the idea of a group representation. A group representation is a particular kind of group homomorphism. This time, it is a group homomorphism, let's say group representation of some group G is the group representation of a particular group G is a group homomorphism from the group G to the group of linear operators on some vector space V. I think this is a notation I've used in my book. Okay. These two are very different objects, right? This is a set of all linear operators on some vector space V. This is some group G. Let's say this is SO3. Okay. This is the set of all linear operators on some God knows what vector space. It can be a Hilbert space, infinite dimensional. It can be some finite subspace of a Hilbert space, and so on and so forth. And of course, you can think of the set of all linear operators on a particular space, vector space V, as a group also, right? Because there's obviously the identity operator. I should say it's an invertible linear operator. Invertible because you have to talk about inverses also, okay? So I should rephrase what I'm saying. This is a set of all invertible operators on some vector space V, okay? Obviously, the set of all invertible operators on some vector space V satisfies the basic group axioms, and so therefore this set is also a group, okay? And you can think of the multiplication in the obvious sense. When you have two operators acting on some vector in the vector space, this is just interpreted in the obvious manner. This is interpreted to mean because T is a mapping, linear mapping from V to V. So it turns something in V into something else in V. It turns V into some other vector, right? So B first acting on V is some other vector in the same space V. Then you use A to act on it, producing yet another vector in the same space V. So A times B is obviously within the set of linear invertible operators. If both of them is invertible, then the composite is also invertible. Okay, and so on and so forth. So you can think of this thing as a group. So then a group representation is just then the group homomorphism between the original group and some set of the set of invertible operators on some vector space V. Now obviously there are many vector spaces that can play the same role, so that we think of many different representations for one and the same group G. And this is very important because in quantum mechanics you will come to learn all the many different representations of a rotation group, for example. Okay? So this is called a group representation. Now, as I said, since a group representation is just some group homomorphism, the mapping does not have to be one-to-one. In the case, if the homomorphism is one-to-one, then you speak of a so-called faithful representation. One-to-one, faithfully mapped from one thing to the other. Okay? Yeah.
Two questions.
Yes.
Is T on V the same as the dual space V?
No. A dual space on V is a function on V. A dual space on V is the set of all functions on V, which means a function means you take something in V, makes a number out of it. This is somewhat more general. This is mapping from V to V, not mapping from V to the set of real numbers. That's a function. This general linear operator maps something from V into something else in V. Something in the dual space map something in V to some real number. That's a difference. That's a dual space.
So the second question.
Yes.
Given a vector space,
Yes.
instead of all linear
Invertible operators.
linear
Yeah.
operators, can you always find a group that is represented by that space?
Oh, that's a very interesting question. Not always. Okay. And so this is a basic mathematical. Rather, the question is asked the other way. Given a group, how many different representations can you find out of it? Okay, because after all, what you're interested in is the group. And that's not an easy question to answer. Okay. You would like to know, for example, whether there are any unitary representations on a group, whether there are this or that kind of representations on a group, okay, and so on and so forth. And that's more pertinently, what are the so-called irreducible representations of one and the same group? So I will introduce more specifically the idea of an irreducible representation later, but I just want to bring up this notion of the representation first, okay? Now, having said that, let me bring you back right away to the unitary representations that we had talked about just last time. Remember, we talked about a rotation group, right? A rotation group is SO3, and the things that live in SO3 are 3 by 3 orthogonal matrices. So the things that live on SU3 are rotations which are represented like so. You represent a rotation in three-dimensional space. You specify a rotation in three-dimensional space by identifying a particular axis of representation and then telling me how much you are rotating, how much angle you are rotating. Okay, so a particular rotation in three-dimensional space is specified by these things. Okay, there are two angles that are required for the specification of the direction. This is a unit vector, and then there's one more angle that specifies the amount of rotation. So altogether, rotation in three-dimensional space is specified by three angles. You can have other ways of specifying it also, but no matter how you do it, it requires in general three numbers for the specification of a rotation. And we already see from the case of the infinitesimal rotation that the infinitesimal rotation A, which is not too far from the unity, is written like this, where epsilon is an antisymmetric matrix of small numbers, an antisymmetric matrix, 3 by 3 matrix. So an antisymmetric 3 by 3 matrix always has three independent numbers. So again, you can see that there are three parameters for a particular rotation. Okay? Now, but then this is obvious. You know, the SO3, what does this thing consist of? This consists of the infinite set of all possible rotations in three-dimensional space. So each one of which is a 3 by 3 special orthogonal matrix. Okay, so G, SO3, if G is SO3, then G is the set of all 3 by 3 special orthogonal matrices, each one of which specifies a different rotation. You have a question?
Oh, no.
Okay. But then, you know, we also talked about this, rotating a wave function. Supposing you have a wave function that describes the motion of an electron in some Hilbert space, right? So last time, what did we come up with? We came up with this unitary representation. It says that the unitary representation of this rotation is equal to exponential of minus I over h bar aj. For the case of rotation, it's theta n dot L, where L vector is the three components of the angular momentum operator in quantum mechanics. Okay? So this one would be, you can think of this one as theta times the component of the unit vector n along the first direction times Lx plus the component of n along the y direction times Ly plus the component of the n direction along the z direction times Lz. This is what is meant by this n dot L, okay, in 3 dimensions. Well, what is this? This is the set of unitary operators acting on the Hilbert space, the space V, which in this case turns out to be the Hilbert space that describes the particular physical system, which is, let's say, some one-electron physical system. Okay, so here's the thing. This is what is called then a representation of the rotation group, because the vector space that this thing acts on is in general an infinite dimensional space, whereas the original rotations works on three-dimensional vectors, right? The representation of a particular rotation then gets to work on this infinite dimensional vectors. Yeah, please. Thank you. Now, in a quantum mechanics class, you don't usually care too much about the mathematical kind of intricacies of this kind of distinction in here, but I think it helps if you mathematically understand it in this way, because a lot of times, myself included, when I was first introduced to this mathematical, quantum mechanical notions of angular momentum operators and so on, and you're told that angular momentum is a generator of rotations, and then the angular momentum operator, which is a differential operator, acts on a wave function, then you begin to search, what is it that I'm actually rotating? Okay, I'm rotating a wave function, but what does it mean to rotate a wave function? Does it mean if the wave function does it mean, let's say if your wave function, a real wave function that is represented by a funny picture, a mountain of this type, rotating it means turning the mountain and turn it around? No, you don't do that, okay? It's just that when you have made a particular three-dimensional rotation and represent it in this way, then you are said to be rotating that wave function, but rotating that wave function does not mean grabbing that electron and somehow turn that around. It doesn't make any sense, you know what I mean? Or the other question may be, the other thing you might think of doing is to somehow maybe rotate the coordinate system describing that electron, and then maybe your wave function turns out to be a different function, but even that is not clear. What if you're thinking of two electrons, for example, okay? And both of those electrons are living in the same three-dimensional space. Rotating that three-dimensional space does not produce a rotated wave function for you, for the two electrons. Okay? So you have to think about it on a more abstract level like this. And it is, so abstractly or mathematically, it's a notion of group representations that takes care of this. Okay?
Which vector space is the unitary operator?
Hilbert space is in general an infinite dimensional space. Okay? Actually, it's not even as you asked me a question last time, Ian, that are those Hilbert, are those necessarily countable? Not always, although most of the time we do work with countable Hilbert spaces, but that's only because it's easier to do so. In scattering states, then it's a wave function which is not normalizable cannot be an ordinary vector in Hilbert space. Okay. Now, which wave functions are not normalizable? Normalizable means that you can somehow let's say if a wave function is normalizable means it falls to zero at infinity. So what that means is that the probability when you integrate it over all space must be a finite number. We normalize it to be 1 usually. That's what we do in quantum mechanics. Okay? Normalizable, what it means is that if you just kind of for the moment think of this as a one-dimensional wave function, the wave function has to vanish sufficiently fast on both sides so that when you do the integral, or when you take the absolute square and do the integral converges. Okay? So if you have a wave function like this, goes on forever, and that's obviously it's not normalizable. But that kind of wave function is very often. A plane wave function looks like that. The plane wave function is not normalizable. So therefore, it doesn't satisfy this very familiar looking box normalization condition. Yes?
In general, it's not normalizable. Can you take a section of it and can you call normalizable?
Yeah, you can. No, well, you can, but then you're only talking about a...
Section of it.
not even a subspace, a subset. Now, there are a lot of physical situations where all the wave functions are normalizable, such as the solution of a simple harmonic oscillator, for example, where you can count the states, right? So you can actually verify that each, you take your, whatever those are called Hermite polynomials, when those are the solutions of the Schrödinger equation, and you can prove that they're all normalizable, okay? And furthermore, so the Hilbert space is sure, it's infinite dimensional, but it's also normalizable. But if you take the space of an electron, the electron can either be bound, in which case you can count those bound states, okay? The lowest state, the first excited state. But then when the electron is not bound, when it leaves the influence of the nucleus, for example, and it works as a free, and it behaves as a free electron, those are called scattering states. Scattering states, since they can be anywhere, are not normalizable. They're not bound anymore, okay? So the Hilbert space concept is not really sufficient to deal with those non-normalizable spaces, non-normalizable states. And here the mathematics become very tricky. There are two paths to follow in general. One is to use the so-called the Dirac delta function approach and force some kind of rules on it. Physicists use it all the time because it's easy to use and it's physically and intuitively quite clear. Mathematicians don't like to do that. They come up with a more formal kind of a procedure, and then I won't go into details because I don't understand it too well myself. It's called a Galfand triplet or something like that, which is what is called a rigged Hilbert space. They have to rig it up in in a certain way to make it workable. Okay, and we won't go into those details. Okay, I just wanna kind of highlight this notion of a group representation, okay? Actually, let me just go one more example. An example, where those of you who have learned some quantum mechanics will come to appreciate as a representation of a rotation group. Now, I can tell you without going into details, although we may have time to prove it later, that for the rotation group SO3, there are infinitely many irreducible representations, infinitely many. And each one depends on what's called the total angular momentum quantum number of the system. And for each value of J, where J can either be a half integer or integer, there is a distinct irreducible representation. And so, let's say for an electron, right? And let's say for a 2-electron system, okay? Each one of which can have some orbital angular momentum, and each one also has a spin angular momentum. And you can combine those angular momenta in various ways. So you come up with some total angular momentum. And in quantum mechanics, you know that the J, which is the total angular momentum, can take on a whole bunch of values, in fact, infinitely many of them. 1/2, 1, 3/2, 1.5, that's 2, 2/2, that's 5/2, 6/2, that's 3, 7/2, and on and on and on and on. So there are infinitely many representations. Do you recall that fact? And now this is called total angular momentum. But then you see that the Z component can have 2J plus 1 values, right? So if total J is equal to 1/2, the Z component, which is called an M number, can be either 1/2 or minus 1/2. In this case, how many are there? 1, 0, and minus 1. In this case, there's 5 and so on. It's 2J plus 1. So we say that each of these irreducible representations is a 2J plus 1 dimensional representation. Why? Because if you take this operator, rotation operator, and act on a wave function for a particular J, okay, let's say I use it to act on, when J is equal to 1, I use it to act on this guy, for example, okay, where the first integer stands for J. This is a so-called bracket notation or bracket notation, Dirac notation in quantum mechanics. This is the M value, and there are three such states, which actually span a subspace, okay, which actually span a subspace in an irreducible subspace in the sense that if you use this operator to act on any one of these, you only get back linear combinations of those. In other words, you can't take it outside, so to speak. Okay? You rotate it in this sense, you get back a linear combination of these. Okay? So in this sense, each of these representations is called irreducible. Obviously, there are infinitely many such. And so we speak of infinitely many irreducible representations for the group SO3. This is one of the wonderful, most important results for the representation theory of SO3. And that's the basis of quantum mechanics. When, anytime you have to deal with rotations in quantum mechanics, this result comes in. Okay? So that's another example which we'll kind of clarify later on. But first, let us get back to group theory, sort of abstract group theory. And so what we are going to do, the strategy that we're going to pursue, and that's very often a mathematical strategy also, and that is to understand the function, the mathematics or the properties of a certain group. You begin by investigating the infinitesimal generators of that group first. For the simple reason that you build up finite rotations from infinitesimal rotations, okay? You build up a finite group element from infinitesimal elements through the so-called exponentiation procedure. And as I mentioned already, the infinitesimal generators are called the elements in the the elements in L are the basis of a certain vector space. That vector space is called the linear algebra corresponding to the particular Lie group that we are studying. Okay? And so if you know the action of the infinitesimal generators through a certain exponential operator, then you can build up all the infinitesimal rotations to give you a finite rotation. Okay? So we begin by studying the properties of the infinitesimal generators first, which means we begin by studying the properties of the Lie algebra corresponding to a Lie group. Okay? And in terms of the mathematical notation, and this is followed by physicists also, if a group is written with a regular capital letter like that, then the Lie algebra corresponding to that group is usually written by the corresponding script letter. Okay? So somehow this was notation that's very often followed. And I guess, since, let's say I'm dealing with this group in here, then I write the Lie algebra like that. Okay? Now, mathematically, this is just a group. This is not a group. Okay? It's an algebra. So that means it's a more complicated kind of category than a group. Why? Because it admits different kinds of operations. Because this is a vector space, so it admits of an addition operation, like any vector space admits. Okay? And you can also multiply elements in there by numbers to get you other elements and so on. But it's not only a vector space. Otherwise, we would have called it a Lie vector space. There's no such thing. Okay? We call it Lie algebra because we introduce another multiplication operation. Okay? Such that both the addition and the multiplication sort of has the identity in it, just like the set of real numbers when we think of addition of real numbers, multiplication of real numbers, okay, and there's there is what's called a zero element, identity element of the addition, and which is the number 0, and the identity of the multiplication, which is number 1, and so on and so forth. So we refer to the set of real numbers as forming an algebra, okay. Now, in this case, not only do you have the addition of the Lie group elements, because you can clearly add together angular momenta, you think of it as vectors and add them together, but you can also think of a way of multiplying these Lie algebra elements also. Now this time the multiplication is defined quite uniquely, okay? You can think of them as operators. Well, actually, you can think of them as, in the case of SO3, for example, you can think of the representations of SO3, which becomes matrices, which becomes operators, first of all, because they're acting on matrices. And in particular, if you think of irreducible representations, they're acting on finite dimensional matrices, so that the matrices, so that the operators become matrices, okay, by representing them with respect to a certain basis set, okay? And then you can think of the multiplication between two Lie algebra elements as being the commutator of those two operators, okay? So you're given two elements, A and B, of a Lie algebra. Then you define very formally, this is called the multiplication of two Lie algebra elements as being equal to the commutator of the two elements. And it's not necessarily zero. So that forms a multiplication rule of the Lie algebra, okay? So the Lie algebra is a vector space, and it has this multiplication property attached to it, and so therefore it makes the vector space an algebra, so to speak. You can add any two things. You can multiply two things by this way, okay? And the addition has its identity, which is the zero, and the multiplication has the identity also, which is the identity operator. Yeah?
So what is the operation between A and B like?
Defined to be the commutator of these two matrices.
Like the first term, like is that like a standard operation?
A times B as matrices. You think of them as matrices. So the first term is A on the left, B on the right, the product, and the second term is B on the left, A to the right. And since matrix multiplications do not commute, this is not necessarily zero. Whatever it is, it will be another matrix. Yeah?
Just to make sure, you said that the algebra is a linear algebra, right? It's a vector space.
It is a vector space, but it is also something else other than a vector space, because it has this multiplication operation that's attached to it. That makes it an algebra. Okay. Now I don't know if you're a mathematics major, you will have learned way back in algebra 1 what an algebra is. What are these different algebraic categories, right? What's a group? What's a ring? What's a field? What's a vector space? What's an algebra? All these things are somewhat different. I get confused by them. Okay, you can tell me what. Ian can tell me what it is. Okay, we just use these terms and try to appreciate what are the most important things that we work with. The multiplication property of the algebra. Okay, and understand that since it's also a vector space, you can add things inside of the algebra also, and you can multiply things in that algebra by a certain real number and get back the same things in the same vector space. Okay? Is that confusing enough? Hope not. Okay. After all, it's quite straightforward in a certain sense. It may be a little bit unfamiliar, but I hope you'll be dispelled of this feeling of unfamiliarity once you have taken a course in quantum mechanics, because in quantum mechanics you come across these commutators all the time. What's the most famous one we talked about last time? X and P. They do not commute. It says that commutator of X and P is IH bar. It only commutes with H bar is equal to 0. That's why we say that in a certain sense H bar is equal to 0 is the limit. It is a limit of quantum mechanics which becomes classical mechanics. But as to how to take that limit is not entirely clear. Okay? All right? In classical mechanics, there's no uncertainty. You can tell the position and momenta absolutely accurately, at least in principle. Okay? You can think of measuring those absolutely But in quantum mechanics, you're not even allowed to think that way. It makes no sense. You can all boil it down to saying that it makes no sense to think of a classical trajectory. You cannot follow the path of an electron. If you could, you can imagine yourself to be a little green man, infinitesimal, and ride on the back of the electron and follow it. Okay? And there's another little green man that rides on another electron, and they can talk to each other, and then and there it is. You can distinguish between the electrons, but in quantum mechanics, you're not even allowed to think that way. Okay? And that's rather revolutionary. That has very serious consequences. As you know, much of the foundation of quantum mechanics is based on the uncertainty principle. Okay? The inherent indistinguishability of identical particles, and so on and so forth. Okay? Okay. Time to take a little break.